And now, Christoph Ortmann, Vice President for HiL Applications, will explain how AutoHawk, VI-Grade's new HiL solution for automotive applications powered by Concurrent Real-Time, can represent a powerful addition to the system engineering process for vehicle development to be used across the entire product development cycle from concept to sign-off. Christoph, come up on the stage.
So, hello, good afternoon, everybody. It's my pleasure to talk to you about hardware in the loop, powered by Concurrent Real-Time, of course, and in particular introducing today AutoHawk. Why do we look at hardware in the loop? Well, don't worry, I will not read the entire statement here published by Frost & Sullivan on a report on the HiL market. Instead, I would like to summarize the essential pieces from that. So the summary kind of is like the HiL market is sizable, high growth market, which is critical for driving innovation. It is aligned with the industry trends for electrification, of course, but also for the introduction of advanced driver assist systems. And how we look at it, of course, is it's synergistic to simulation and simulators. And that's why we would like to leverage our core strength and provide high-class products and services to help our clients to drive their innovation. Initially, we want to focus on three main application areas. And you will see more solutions developed over time in the area of chassis engineering, including steering systems, passive and active suspension components, also, of course, include our brake systems, and all of that, all the associate controllers that come along with that. Then the other topic is ADAS, AV. We heard a couple of nice additions now in our tool chain on the software side in VIA WorldSim. And we will focus there, of course, on sensors, cameras, radar, LiDAR, and how we deal with that. And then there's application areas around powertrain, in particular about electrification. And of course, this is not a real secret to anyone, but the whole trend of electrifying the vehicle has major impact also on other subsystems, like the steering subsystem or the brake subsystem with recuperation of energy. What does it really mean is, to develop any of these features or functionalities, the overall model landscape or the model is becoming ever more complex. So you have a need to run large compilation of models, with model in the loop, software in the loop, hardware in the loop, and in a vast variety of combinations of all of that. So what's our vision in that? And I think you heard it already a couple of times, but I want to reiterate that anyhow. The vision is to have an integrated virtual test approach, where hardware in the loop, of course, is an essential part of it. The application allows our customers throughout the development cycle to decrease the number of physical prototypes and to achieve virtual sign-off in the end. Of course, during product development, controllers and hardware components become available and need to be included for simulated testing activities. And I want to touch on that a little bit, perhaps in more detail. So one thing we observed, of course, a lot is, you may want to do everything in software, that's clear. You can do it early and everything, but if you work with a supplier, I'm now naming an example like Bosch Conti, without blaming anyone, but you may not even get the software from them to be included. And the only way then to have an accurate representation of a vehicle is by including a real controller. You need to put an ECU of a real system into the game. And we see that increasing, actually. The complexity is increasing over time. So VI-Grade HiL solutions enable customers to use the same real-time tool stack for different simulation activities, software in the loop, model in the loop, hardware in the loop, on the simulator, in the vehicle, in the lab. Now I'm proud to show you something new here we're introducing today. Today, I'm proud to actually stand in front of you here and that I can announce the launch of the new AutoHawk powered by Concurrent Real-Time brand that we introduce into the market. What does it mean, roughly? In a nutshell, summarizing on a higher level is, it's an AIL solution powered by Concurrent Real-Time for automotive applications. It consists of real-time hardware, real-time operating system and software, the associated I/O boards, etc. It can be freely configured with VI-grade real-time software or third-party software for that matter, all on the same configuration. It can work as a standalone Linux-based high-performance computer if you want, as an HiL system, or in combination with a driving simulator or on the real vehicle. So in other words, AutoHawk is a flexible HiL platform that can be used across the entire product development cycle from concept to sign-off. Let me start out with talking about a couple of solution highlights here. AutoHawk hardware is based on commercial off-the-shelf components, this famous COTS kind of statement. But what does it mean for you? Of course, it means that we can adopt new technology that are available in the market segment much sooner and at a pretty attractive price point. The leading real-time operating system that we have is based on Linux and provides an open architecture which makes the integration of your custom solutions, but also of any third-party solution and products, even I/O boards, much, much easier. But probably one of the most attractive details is the multi-core technology that provides for more computational power and allows you to run very complex models and controllers all in one system, avoiding the problems that you may have experienced previously by putting smaller systems in a network kind of relationship. Simulation Workbench runs on that. It provides the platform to integrate models. So the solution does not really require Simulink, but however, it is really a highlight that it's so tightly integrated with Simulink that in fact you can run it all on the same machine. So you don't need, if you don't want to, have a client in which you work and then transfer the code onto the host system. It is using or supporting common automotive communication protocols, CAN, FlexRay, etc. It is, of course, supporting the AutoHawk. AutoHawk is, of course, supporting the VI-certified ecosystem. And the open architecture that we have with ASCII data structures, configuration files, as well as the C, Java, MATLAB, Python API, all make it very easy to integrate with already existing in-house tools and processes, for example, for test automation or data logging. Last but not least, it's VI-grades and Concurrent's multi-year experience to connect HiL systems with simulators that make the solution also of complex systems possible. Now let's take a look how we want to use that along the process, really. So in the first stage, for example, you may use it as a desktop system. You can refer to that as offline, software in the loop, model in the loop. So in other words, AutoHawk is used for offline simulation, regular controller development, and then also taking just advantage of the sheer speed of the system for design of experiments and optimization loops. What's the benefit of that really at that stage is use the same machine and tool stack that can be used for HiL and driver in the loop later. So you get, in other words, already from the beginning closer to simulator and HiL applications with a reduced investment. You can share the tools and the hardware in the process. Then comes more the traditional approach, which is the in-lab, I would call it, approach with hardware in the loop, software in the loop, model in the loop. So these are typical HiL applications in which a device under test, an ECU, you have seen steering rigs and all sorts of devices under test are connected to AutoHawk and running in real time. You may use it also with fault injection. Test automation is also possible if needed. The benefits, well, during this phase, the device under test can be tested prior to connecting it to a driving simulator for further tests, for example. On the simulator, that's the next application area, of course, where, so in other words, you have HiL, driver in the loop, software in the loop, model in the loop. So these are the HiL applications in which the driver sends an input to AutoHawk through the simulator. This could be useful, for example, to test corner cases and where the closed-loop inputs are essential. And then you have the on-vehicle scenario as another interesting application. Well, in that case, there's an entire vehicle model running on the vehicle, if you want. And because you have such a high performance available, car real-time, for example, can run 5 times real-time. And so you can actually have a controller concept where part of the sensor signal comes from a virtual vehicle model running there and from real sensors on the vehicle. And that is something that opens the door to totally new approaches for different controllers. And last but not least, I mean, we're aiming, I guess, high is for the digital twin, where the driving simulator and the real vehicle are fully synchronized and are affecting each other. So, moving forward, we've decided to package it in 3 major kind of standard packages, also to make them available faster to you if you need some. They come, so to speak, in 3 sizes. We kind of distinguish between them through the number of cores. So with 18, 16, or 24 cores, they're all equipped with a pretty decent size 2 terabyte disk, which is able to manage projects, but can be used for data logging pretty much. So you can also look at that as a data logger to some extent. All systems come with a communication card supporting CAN, CAN-FD, LIN. All these systems, of course, run Linux with RedHawk as an operating system and Simulation Workbench as the integration platform. And for on-vehicle application, I should point out that these chassis also can be put into ruggedized chassis. So, of course, these are standard components that enables us to be basically faster in production and getting them to you. But also they are highly configurable and expandable. I want to highlight only one of many examples of that. So each of these systems come with 4 to 7 slots that you can use to expand with I/O boards. Probably the most versatile I would like to mention is the freely programmable FPGA, which gives you a lot of extra flexibility that you can use to program anything you want on an FPGA board. Also, I should mention, which is not seen here in this image, is an expansion chassis for signal conditioning and fault insertion, along with a programmable power supply, which you see a little bit here on the top there. So we thought about why we put these 3 categories in place along applications mainly. So what's driving the sizing of the machine? And we thought about, okay, typically the AutoHawk with 8 cores would be suitable for regular kind of offline simulations with car real-time, for example, for DOE optimization and these kind of things. Standard kind of simple ECU testing, and for using it to connect to a chassis HiL like a steering rig or something like that. That's a typical use case that we foresee for that size of a system. Then we have the 16-core system that allows you to have more cores available that enable you to add more advanced tire models, for example, which need individual cores. And you can also use it, for example, for WorldSim, where you have more agents and therefore you have more need for computational power. Last but not least, we have, of course, a really high-end system with 24 cores that is, for example, suitable if you have really high-end multi-body simulation models, so kind of like Simpac, Adams, these kind of really high demanding models, or you need them for in-vehicle testing. So any kind of complex case, that's where we foresee the application of these systems. Another way to look at the AutoHawk package or solution is it always consists of a hardware component, basically the well-proven real-time system that we also have already used for many years in our simulators. It comes with a software, including via DriveSim with a vehicle model, virtual driver, and via car real-time, via WorldSim for the scenario, sensors, environment, etc. And of course, you can run third-party software and extending them system through the FMU interface if needed. All that is integrated with the powerful Simulation Workbench and its underlying real-time database. So they kind of serve as a if you want a bus system in which you can exchange signals, as most of you probably know from the application on the simulators. So users may choose to automate testing, either using the simulation workbench scripting capability or connect to existing test automation tools through the available APIs that I mentioned earlier. The device under test is then connected through, for example, a CAN system or specific I/O boards. And in order to get the human in the loop, the system can be integrated with a simulator, which provides great value, for example, defining and testing corner cases. Let me introduce to you a demonstrator that we have prepared and that you can see outside. I think probably most of you have already passed by. So what does it really include? We've chosen a scenario that you want to basically develop the functionality of a control system and validate it, and subsequently even calibrate it, the system demonstrate how a system like this can be used to get the controller better prepared before connecting it with a simulator or before getting it on the track. So that's kind of the use case that we have had in mind out there. We are using the proving ground that is available in VI WorldSim. The maneuver is a simple lane change maneuver that is often referred to as a press maneuver. And because it is normally used to rank cars with the quickest time to go through the cones actually against competitive cars. The system out there is based on an AutoHawk 8, and for the purpose of displaying animations and results, etc., we also include the normal Windows PC into the system. Normally, you could find an expansion chassis or something like, or signal conditioning on board chassis in that location where the PC is right now. We have used a programmable off-the-shelf ECU, so nothing spectacular, an ECU that we can put any type of controller on, like an eDrive controller, or we chose now a normal ESP controller. And when you go outside, the control system that we have, of course, acts on the brakes, and it guarantees the smooth transition through the cones. And of course, you can also turn the entire action off. So I invite you, of course, to come outside and take a look at that demo. I just will flip through a couple of cases, and I'm doing that also to encourage again that you take advantage of the fact that we have our partner companies out there. So for instance, we are having a case where we have a concurrent system connected to a steering rig. That's presented by Mechanica 42 here in this case, and I have to go through the time here quickly. You can also connect a brake system. We've seen in recent publications at our conference from Volvo that they have successfully done that already, proven that the technology works really well even for complex scenarios. Perhaps another highlight is a cockpit that was developed in the recent years that contained more than, I think, 10 ECUs altogether, so a very complex network of systems with different kind of CAN networks on the same machine. And in the area of ADAS, I invite you again to go out there and visit the different demonstrations for the integration with cameras or radar, etc. So I'm going to go through that rather quickly now. And perhaps something as an odd kind of thing that shows you a very custom solution that is also available. This is for a really computationally heavy scenario that was put even in a rugged kind of big rack that can be put on the vehicle for testing on the vehicle on a rough road. So that's an example here for powertrain. And let me conclude in the last 40 seconds that I have. So HiL applications complement offline and driving simulator activities and help to achieve virtual sign-off. The demand for HiL applications is expected to grow in the next 5 years by roughly 80%. with the automotive market responsible for a significant portion of that business. And ViaGrade, together with Concurrent Real-Time, have launched AutoHawk with a complete and open simulation made of hardware, software, and of course, we're providing the integration service for that. With that, I thank you for your attention.